Okay, so today, of course, the focus on the take-home midterm that I guess I'll be ready to post it. Probably, I mean, I know I said tomorrow, but I think it'll be ready tonight. So that can give you even more time.
Wait, what?
Wasn't it due? I
Posting it tonight.
thought the chat,
Oh, we have more time.
isn't the chat due Friday?
It is. I'm not talking about the due date. I'm talking about when it's posted for you, so you can start.
It's not gonna like, so it's just posted.
That's what I guess, yeah.
Oh, yes, but let me talk about that too.
I'm not ready to start.
You don't have to start when he posts it if that's not your preference. He's just allowing those who want to start early to start early.
Yeah, because it's gonna be due at the same time as it originally was. So this is not creating an unfavorable situation for anybody. Okay.
I'm still stuck on homework.
So we can talk about homework as time permits, after any questions related to the midterm have been addressed. Okay. So as far as midterm is concerned, okay. So I've had to change some of the questions like in the practice, so I gotta do the same thing for the real one. Still do Friday. 6. Now, what I will post. Okay, so the PDF, like for the practice, and for those of you who want to take advantage, a LaTeX source file that goes with the PDF. Okay. So those of you who have LaTeX experience, if you want to LaTeX up your answers, instead of writing them out on paper, then you can do that. Okay. Now, okay, so things that'll come up, and this is consistent with what you've seen for practice. Okay, so determining rate of convergence, of a function that base h goes to 0. And then as part of that, Taylor's theorem would come into play. Also, if you're given an expression that incurs catastrophic cancellation, algebraically rewriting the expression to get rid of the cancellation. The point by the section. And then if you interpolate a polynomial in either Lagrange or Newton form. So Newton form would involve finite table. And then concept check questions from these same sections. There'll be 10 questions in all, that kind. Okay. Okay, here's an example about eliminating catastrophic cancellation. Something like this, if this difference quotient right here, if h is really small, so sine of something close to x minus sine of x, so that's going to be nearly 0, and then the denominator is also there's zeros. So this difference is going to be small and will suffer cancellation. So this subtraction will be inaccurate because there's going to be some loss of precision. And then, so whatever error here, you're dividing by h, which makes the whole fraction larger. So the error is actually, the absolute error is quite large. So what you can do is you can rewrite this numerator using a trig identity. Now, if I use a trig identity for the sign of a sum, so then I get this using that trig identity, and then I can break that up into I can break it up into two fractions. So I have cosine x sine h over h. There's no subtraction here. And then I have plus sine x times this fraction right here. Now, can anyone tell me why this fraction is a problem? Cosine h minus 1 all over h.
You know what h is, or
What?
cosine of h being 1.
Yeah, or nearly 1. Yeah. So this also suffers from cancellation.
Get almost 1, so 1 and 1.
Yes. Yeah. So, but this is something that we can do something about because we have, this is actually a half angle formula. That you can write this fraction in terms of sine squared of, so whatever angle you have here, you have half the angle here. So now the subtraction is removed altogether. So then you can replace this fraction with this one, and then the cancellation has been removed. So there's no more problematic subtractions. Okay, so any questions about how this particular cancellation issue was remedied? Okay, here's an example of rate of convergence. You're given this expression, sine h minus h plus h cubed over 6 all over h to the 4th. So what you can do, first is you got to find out what the limit is as h goes to 0. You can use any technique like from calculus 1 to get that limit. For example, L'Hopital's rule. So I'm repeatedly differentiating the numerator and denominator. And as long as I keep getting 0 over 0, I keep differentiating. Eventually, what you find is that the limit is actually 0. So then, now that the limit is 0, we need to see what the rate of convergence of this is. So you replace sine h with its Taylor expansion around 0. So what I've done here is sine h is replaced by this, and you want to make sure to include enough terms in the Taylor expansion to possibly cancel with terms here. Like here are terms that I've included here go up to degree 3, so I can at least go 1 past that. Include this term as h to the 5th over 120. So now, after I've replaced sine h with this Taylor expansion, then I simplify whatever I can, and that's why I get h to the 5th over 120th plus higher order terms. And then I divide all that by h to the 4th. So it turns out that the rate of convergence is big O of h. Reason why is we have h to the 5th up here and h to the 4th down here. So really this is equal to, I can write this as h over 120 plus big O of h cubed. Okay, but the term of rate of convergence is this one, h over 120, so it's big O of h. So this is the final answer, the rate of convergence. Any questions about that?
How did you get the sine h?
Well,
How did you get the sine?
That's given. And the original expression that I want to find a rate of convergence of had the sine h. So this is our starting point.
H minus h3.
Yeah, so sine, okay. This right here in square brackets, that's the Taylor expansion of sine h. So this whole fraction here is equal to this with sine h replaced by this Taylor expansion. So that's how these kind of rate of convergence problems are worked out, is if you have a function like sine h that's not a polynomial, you replace it by its Taylor expansion, which essentially is a polynomial, and then you can simplify to get the rate of convergence. There was a problem like this on the homework 2, where you had the exponential, e to the h, and that was replaced by a Taylor expansion. the same approach.
Approach.
Yes, it's, so, yeah, if you look at. It was, this homework problem that I believe you did. Here, it's also rate convergence problem. In this case, the limit is 1, so you move 1 to the other side, and you replace e to the h with its Taylor expansion, and then simplify terms, simplify as much as you can, and then you get to rate convergence.
So when is it the time to use big O notation and then to use the
Oh, I didn't use that one.
in the solution?
What?
In the,
Oh,
practice test that's similar to this question.
Oh, let me check.
It's whatever we're already real now.
Wait. I don't see.
Is a problem?
Are you talking about this?
Yeah.
Are you talking about squiggly?
Yeah.
That's not an epsilon. That's exceed.
Oh, I thought an epsilon too, but earlier.
Yes, and that's why I reading it's a squiggly.
Okay, so squiggly.
Wait, I'll come back to this. Okay. Oh, yeah. So you're talking about like the remainder term?
Yeah.
Okay. If all you care about is like rate of convergence, as in it's big O of something, so you're not really concerned with constant factors like this 1/120th, then you might as well just do this. Now, by contrast, okay, one of the homework problems, that was actually also from homework 2. It was this one. This one right here. The goal was to actually get the remainder. So in that case, you need to keep everything.
So is the one that you were just going over in number 3, are those not asking the same thing?
Okay. Okay. They are asking the same thing. So as far as getting the rate of convergence. Okay, I see what I did here. Shoot. Okay. Oh, now I feel like I messed up. What we see here is a sufficiently rigorous approach to proving the rate of convergence, because you had to show, you weren't trying to show that your expression, your function minus your limit is bounded by a constant times whatever function, like h squared. And by retaining the remainder, the Taylor remainder, you can actually get a hold of what the constant is.
Right.
Okay. So here's where I've messed up. So in this case, here I've not produced a constant, saying like, okay, this expression is less than or equal to some constant times h. Now, you can say that whatever the constant is, could describe it as 1/120th plus something else. Where I'm not showing that something else is. Okay,
My question is when, like, if these questions are asking the same thing, when do you
Yeah.
want to use them together?
okay.
And prove that it has that constant, or it
yes.
doesn't.
Okay, the reason why I'm saying I messed up is what I should have done right here is use the exact same process as in what you see in the practice test.
Mhm.
Where instead of having big O H to 7, I actually have a Taylor remainder here.
Mhm.
So that I have a rigorous bound on what the constant is.
Okay, so,
So in other words, I guess after showing you all this, I'm not gonna tell you to ignore it. Well,
But we're just ignoring the last part,
yeah, in other words, instead of having a big O H to the 7, which is a bit sloppy,
right? Getting this.
I should have a Taylor remainder. I should have used a Taylor remainder right here. And then I'd have some constant, which would include this 1/120th, but there'd be something else there.
so that would be preferred what you'd wanna see on the test, on like working.
Okay. I'll get you a square.
No, it's okay. I'm not like pushing you. I'm just making sure I'm in this race. Sorry.
Okay. So now I have to decide what I'm really going to require. Um, okay. So in relation to this problem right here, what I will accept, because it'd be terrible of me to show you something and then tell you you can't do it. And I fell into that trap and I'll have to live with that. So option number 1 is you proceed exactly as I did here, where you take your Taylor expansion out far enough so that whatever terms can be canceled are canceled, and you get something like a fully defined term like this h to the 5th over 1/20th that doesn't cancel with something else. And then you can use big O to refer to the rest. So that you end up with this because this term is explicit, like there's no fudge factors or anything like that, then and because this is big O of H cubed, it would be correct to say that, I mean, it's sufficiently rigorous for me to say that for you to conclude that the rate of convergence is big O of H. So in other words, if you do something like this, I will accept it. Okay.
This is like a silly question, I guess, but is it possible to stop before you get to the big O of H? So where the H over 120, stop at that part, the H over 120 plus OH3 in, just one before you say.
Oh, so in other words, don't have this.
No, don't have the end, very end.
Oh,
Don't have the O of H, just have the.
okay. Well, I want the final answer to be big O of something, because that's how rate of convergence is stated. Rate of convergence is big O of whatever. Okay. Okay, well, then we should deal with that. So,
I guess.
So what's Thursday gonna consist of?
Arbitrary, but
hold on.
how we go from having an H and an H cubed to just an H with no subscript versus.
Oh, you're wondering why this is an H cubed? Okay, remember what I said when I first covered this topic? The lowest power of H determines the rate of convergence, not the highest.
Okay.
Because the reason why is H is going to 0. When H is small, okay, this is small, but H cubed is far smaller and therefore negligible.
Yeah.
Yeah, so, the exponent that is closest to 0 wins.
Okay, that makes sense, I
Okay.
think that was just it.
Okay, okay, Morgan?
You actually said something that clarified it for me, so we're good.
Well, that's where we're leaving. Okay, Thursday. There is no class on Thursday. We ain't meeting. Class does not meet on Thursday.
But do we still have office hours?
I will be holding office hours from 1 to 4 p.m. as usual.
That's a good.
I remember a question I had from earlier then.
One.
So once you post a test, you said we can only ask you questions about clarity for the test, but if we wanna ask you something about the homework, which is a concept that's on the test, how does that work?
Well, you can ask the same kind of questions about homework then, you can ask it anytime.
But we can't ask you about questions
He's
that.
not gonna give you the answer each way, it's just,
Huh?
he's not gonna give you the answer.
Well, yeah, but
Oh,
give the
not
answer.
allowed to
Help
ask
us.
about things.
Well,
You can ask about clarifying okay, what's the issue?
Just let it be, please.
Okay, they said-
This is very compelling, because I really don't need it right now.
No, it's not that. I don't know. It's not, he's not Dr. Lee.
What is it?
What is that?
Okay,
All
okay,
putting it
so I'll think you do this. So Dr. Lee, whenever he released the test, we couldn't ask him any questions about the homework because the homework were the same concepts on the test. So if we're asking help on the homework, then, which is a concept that's kind of like, it's not the exact thing on the test, but like,
Well, so in other words, if you had asked them about homework-related content before the test was put out, that would be okay, but once you put it out there, then
yes,
it lowers the boom?
yes, because
Okay.
you're asking questions about.
See, why are you saying that to him?
Yeah.
Don't give him ideas.
Because I need to know, except Dr. Lee didn't tell us and I was surprised.
Okay, yeah, but I mean, they're still separate problems. Yeah, so
Because if I still have a question, I'd like to still ask, even, like, it's still on the homework, because understanding the homework, which is also helps with.
I'm fine with that. Okay.
So does that mean we don't need to use the squiggly?
Right, you can do a problem in a squiggly free way.
That's easier.
But, okay. If you're gonna do that though, I do wanna see like an explicit leading term like this. And then a big O.
So, I have a question, it may be silly, but it's not related to that, it's related to practice.
Okay,
On number 2,
wait, number 2 of what?
of the midterm
Okay.
practice,
I thought it wasn't related to a practice.
it wasn't related to that, it was
Oh.
related to the.
Okay, would it be possible to wait until I wanna scroll through this and go.
Oh, yeah, I didn't know.
Yeah. Like, I'm jumping around and worried that's causing more confusion.
Okay.
Okay, alright, are there any questions up to this point? Okay. Okay, here's an example involving interpolation. Right, so like, here's your function, here are your 3 interpolation points, so that would be a quadratic interpolant, here are the y values that go with them. I chose interpolation points so that the y values work out nicely, which is square root. Then your Lagrange form would be your y values, 1, 2, and 3, times your Lagrange polynomials. And then here are the Lagrange polynomials, using the formula that's given. And this right here is what your final answer would look like. Don't simplify it.
Do not lie.
Yeah. It's easier for me to grade if I have it written like this. Because then that shows me that you understand the process of generating Lagrange polynomials. Because the simplifying would give you power form, you could just gone into the MATLAB and done polyfit and got there. So, okay, so that's what you do for like the
Can we talk
Lagrange.
The process, I don't think I understand.
Oh, wait, for Lagrange?
Yeah.
Okay, So your interpolation points here are 0, 3, and 8.
Okay.
So for this first term, the at x equals 0, y value is 1, so we have 1, times Lagrange polynomial that's supposed to be equal to 0 at the other 2 points, 3 and 8. So that's why you have the linear factors, x minus 3, x minus 8. But you also have to make sure that if you plug in x equals 0 into this term, you get 1. So you divide by 0 minus 3, 0 minus 8. So each Lagrange polynomial is supposed to be equal to 0 at all of the interpolation points except for one of them, and which is equal to 1. So, like if I go to the second term, for x equals 3, I want the y value of 2, so I have a 2 there. And since this is the one for x equals 3, I need to be 0 at the other 2 points, 0 and 8. So I have x minus 0, x minus 8. You see the pattern that's emerging here? Working?
Yes.
Okay.
I remember that. So 0, 1, and then 1, 2, and then 0, and then something else. And then 0, 1. No. Yeah. We're good.
Okay. Any other questions about Lagrange?
That version makes sense, I'm just making sure I understand the practice version.
Oh, right. Okay. We'll come back. Okay. Then Newton. This is the same interpolation problem. So x is 0, 3, and 8, and y is 1, 2, and 3. So I fill in the divide difference table. So you list the x values in your first column, y values in your next column. And then you can see here in small font the how the divide differences are computed. So I take the y values of 2 minus 1, and then I divide by corresponding x values, 3 minus 0, to get this divide difference of 1/3. And then I go down here and take the divide difference between these 2 points. So I have 3 minus 2 up here divided by 8 minus 3 down here, so I get the divide difference of 1/5. So my divide differences in this third column are 1/3 and 1/5. So now I subtract them. So I have 1/5 minus 1/3 divided by these x values, 8, 0, 8 minus 0. So then that gives me my final divide difference of minus 1/60. And then I put all of those into the Newton form. So you go across the top row of your divide difference table where we have 1, 1/3, and minus 1/60. So those are the coefficients in the Newton form. So the first coefficient is just by itself, it's just a constant. And then for the next term, you multiply by x minus the first interpolation point, which is 0 in this case. And then you have a minus 1/60 times x minus 0 again, times x minus the second interpolation point, x minus 3. So this right here is the Newton form. Again, don't oversimplify. In fact, what I should do is erase this part, because I was simplifying for reasons that apply well. Okay, so that's what the final answer should look like in Newton form.
Silly
And
question.
you inform,
Yes.
Silly question. In the practice.
Yeah.
Why does it include
Who what?
the solution?
Oh, okay, right. Yeah, I wouldn't say that, well, it's really not necessary. So sorry for any confusion that introduced, it's, because it's, I guess, a way to keep track of all the values that you're filling in. But yeah, those aren't involved in any computation.
can you explain the final name form one more time?
For the final Newton form.
Yeah, the P2 x equals.
Okay, so starting from the zero order divided differences, which are just the y values, you take the coefficients from the top row of your divided difference table. It's 1, 1/3, minus 1/60. Okay, so then first term is okay, constant, then you just put it there by itself. Then what you're multiplying by are linear products of linear factors, x minus each of the interpolation points, except the last one. That will not be used. So because each term has degree 1 higher than the previous one. So first term constant, second term 1 linear factor. It's always x minus the first interpolation point. Listen. Whatever linear factor you have in each term must carry over to the next term. So x minus 0 appears again. And then you'll tack on one more linear factor, x minus the next interpolation point. So you're starting from the top down.
Until you get to your needed number of polynomials.
Yeah, so your polynomial is a degree 2. So once you have a term of 2 linear factors, or once you exhaust your divided differences from your top row, then you stop.
I see.
Any questions about that one?
Yeah, the one that's similar on the review, so.
Okay. All right. Let's go for review. Go for practice. Okay. Okay, this is one about gradient convergence of this function 1/1 plus h, which is an approximation to e to the minus h. So really all I did was think of e to the minus h, that's the same as 1 over e to the h. So then I approximated the e to the h in the denominator by its first 2 terms of its Taylor expansion, which is 1 plus h. So that's where this came from. Okay, so here we're dealing with computing relative forward error and backward error. So you're given an h value in 0.1. So you go ahead and compute the exact value from the exponential. And then that's y0. And then y0 hat is the approximation evaluated at h naught. So now you have your exact value and your approximate value. So now you can go ahead and compute use the definition of relative forward error from your y values. So we have that here. So it's fairly small. Please stop me if there are any questions about anything as I go. Okay, that's relative forward error. Now for relative backward error, so that involves the h values. So you need h naught hat. So remember how h naught hat is defined. That's your input, your perturbed input value for backward error. It's solving this equation. You take your approximate y value, set it equal to your exact function at your unknown perturbed input, h naught hat, and you solve this equation for h naught hat. So since f is e to the minus h, okay, so I'll go ahead and fill that in. So in this case, y naught hat is e to the minus h naught. Okay, so I'm solving y naught hat is equal to this. So just algebraically, this is what you get. So remember, h naught is 0.1. H naught hat is pretty close to 0.1. And that's just something to keep in mind is that your h naught hat should be approximately equal to h naught. If it's not, then something went wrong. So now we have h naught hat. Okay, then you go ahead and use that h naught to compute the relative backward error. which is also small, but not terribly small. So any questions about how you get relative forward error, and especially relative backward?
I'm confused on the y hat equals f of h.
Okay, so y naught is f of h naught. So that's, here we have the exact input and output.
Which we said y,
But y naught hat is the approximate output.
which is the 1 over 1 plus h here.
Yeah, that's how it was computed. But for backward error analysis, you want to set it equal to the true function, the exponential of some, and h naught hat is unknown. You have to solve for it. This was similar to one of the homework problems, also from homework 2, where you were doing approximations involving cosine with second and fourth degree Taylor approximations. So you'd use those Taylor approximations to compute an approximation of cosine, but then you took inverse cosine of the approximation to backtrack to an approximate x value. It's the same idea. I don't know if that answers your question.
Yeah.
Okay, anyone else? Okay. All right, now we have both relative forward error and relative backward error. So the next part of this is use those two answers to get the estimated relative condition number. It's just an estimate. So all it is you're dividing relative forward error by relative backward error, and we see that turns out to be 0.1. So it happens to be roughly equal to the original h value, which is 0.1. Yeah. So relative condition number is this relative forward error divided by relative backward error.
The estimate part, just a simplification of the first part.
Oh, you mean this part right here? That's just fluff. It's not really part of the question. I mean,
You could use it to confirm.
yes, good idea. Okay. After that, repeating this with h not being 0.01, just to get relative forward error. Don't care about relative backward error at this point. So relative forward error with this h naught value, 0.01, you get this value, so 4.710 to the minus 5. So if we go back with h naught being 0.1, you get 4.710 to the minus 3. But then, this is what I talked about last class. So what happened is down here, h naught was reduced by a factor of 10, but the relative forward error was reduced by a factor of 100. It went from 10 to the minus 3 to 10 to the minus 5. So what that would indicate is that the rate of convergence is big old h squared.
For this one on h equaling 0.01, I got 4.97. It still times 10 to the negative fifth.
Oh, that's what you were talking about earlier. Let me check. So
Were those two considered really close?
well, maybe I just mistranscribed or something. Oh, yes, it really is 4.97. Well, I guess I'm fixing it now. Still reduced by a factor of roughly 100. Whereas up here, you did the first one. Rebecca, you also got 4.7 for the first one?
Yeah.
Alright, so I only messed up once.
So are those, so it being 4.7 and 4.97, those are still close enough to then. be able to
Yeah,
compare? Okay.
Okay, so in other words, you're determining experimentally that the rate of divergence is big O of H squared. The last part of the problem is really getting the rate of divergence. So in this case, what you're doing is using Taylor expansion. So first, you're filling in the true function and its approximation, and then just algebraically manipulating to get this, and then replacing e to the h with this Taylor expansion. So then we go ahead and okay, so I took the longer rigorous way to get the constant, but so it turns out that e of h is being bounded by a constant times h squared. So now we see rate of divergence really is h squared, which is corroborated by the experimentation above. So I put this part in to help you check what you do down here. Yes.
Is it necessary to put, like, if you got to 1/2 e to the h squared over 1 and stuff, is it necessary to go any further and be like, all of that extra stuff is c then h squared, and then say the rate of convergence, or can you just say from that the rate of convergence is
Okay. So you're talking about what happens up here?
lower?
Or-
Next,
Okay.
yes, the very last two.
Okay. What I would be fine with is if it still goes to what happens up here. If instead of this, you have the 1 plus h plus 1/2 h squared plus big O of h cubed, and then simplify as much as you can, then what you're going to wind up with is okay. Well, okay. There's one thing I do want to point out though, because then what you have here is something that's it was just the 1/2. There's no e to the squiggly, and then you'd have h squared plus big O of h cubed in the numerator. Okay, there is one point though that's worth making, and this is something I am concerned about. Right here, where I have h squared over 1 plus h. A very important technique for finding upper bounds for expressions like this is that when it's a fraction, that you're allowed to do anything that makes the denominator smaller, because that makes the whole fraction larger and gives you an upper bound. Because so h squared over 1 plus h, if I just neglect the h, so really you can neglect any positive term. If I just neglect h, then I can say that this whole thing, this fraction, is less than or equal to just h squared. Actually, this is a value technique that might sometimes be used for real analysis for proving limits. I guess I probably could have said that before, but I guess a lot of you suffer from real analysis methods. Yeah.
Take mine tomorrow.
What?
Take mine tomorrow.
Oh, okay.
There you go.
I'll trust that I was trusting you all the way up anyway, without me saying anything. Okay. Yeah. But yeah, I mean, I would be fine with. You don't have to deal with a Taylor remainder, including a big O in your Taylor expansion, like was done up above, is fine.
Silly question number 4.
You're counting them.
Yeah, it's not feel better. So is the inequality part is
is that related, like, does that occur in both versions, or is that specific to the squiggly version? and
Oh, okay,
not the other?
there is some bounding needed because in this case, because you have a more complicated denominator. Like for example, that didn't come up in, this one because your denominator was already simple to begin with. This is h to the fourth, you cancel the h to the fourth, you get something nice like this, where when you get an expression like this, it's really easy to say what the rate of convergence is. But when you have something that's a rational function, something like this fraction right here, it's not so obvious. So you make it obvious by dropping the h and saying, oh, it's less than or equal to this. So that's a key skill. And that would come up whether you express your Taylor expansion using a remainder, explicit remainder, or a big O term. It's going to come up either way.
5 of these problems are based on homework problems and other.
Based on homework problems and what you see in the practice. And then the other section of 10 problems are concept check questions, like the quizzes.
The only time whenever we have to do the inequality and do the upper bound is whenever we have a more complicated
Yes,
domain.
yes. And that will come up. Are there any questions about this one?
The test is timed when you start it?
No, I'm going to finish that deadline on Friday night.
Okay.
No,
Yeah.
it's not.
Yeah.
Oh, okay.
Is there a file for the test?
There will be a file posted in Canvas. I will announce it. Are there any questions about this problem? Next one, okay, a floating point arithmetic, there's a cancellation issue. So when you're, first computing it with given h value using a certain number of digits of precision. So what that means is, if you're told to carry out arithmetic using a certain amount of limited precision, that means you must round, or chopping in this case, rounding or chopping, whichever is specified, you must carry that out after every single operation you perform. Like here I have a square root of 6.001, that's from 6 plus h. I take this, okay, so go ahead and use your calculator or MATLAB to compute the square root, but then you take that result and you must round to the specified number of digits, in this case 5. Similar to the square root of 6. So make sure you do that after every operation, see what you're supposed to get. Now in this example, you go ahead and do that 5-digit chopping, the value that you get is 1, but the exact value is 0.2 something, so it was horribly off. So you explain why. Catastrophic cancellation from subtracting these two numbers, square root of 0.6001 and square root of 6, that are close together. And then in the next part, you use whatever algebraic trick, in this case multiplying and dividing by their conjugate, like what happened in the exploration involved the modified quadratic formula. Simplify as much as you can, and you end up with this expression, where instead of subtracting square root of 6 plus h and square root of 6, you're adding that, which is perfectly fine. And then you carry out similar arithmetic as in the previous part, but with a modified expression. Plug in h equals 0.001, still use 5-digit chopping arithmetic, and you get something that is much more accurate. So that's how that one plays out.
With precision being 5, and we don't include, so in this case, we don't include the 0 that's in front of the decimal.
Whoops. Yeah, that should be, hold on. Okay.
Make sure I still have that understanding, that was thinking about it before, okay.
Yeah.
Oh,
Well, okay, actually, you know what? Reason why this should be included is because then I would call this 2.0412 times 10 to the minus 1.
okay.
So in the, think in terms of floating point numbers being normalized.
Okay, that's, so,
I'm not really cheating and getting an extra digit.
well, okay.
Yeah.
But in this one, since the.
Yes?
Silly question. So is the conjugate more, effective because you're no longer subtracting?
Yeah, because, subtracting close numbers is bad. Addition is always okay, because it doesn't occur against it. When you're adding numbers of the same sign, there's no cancellation. Yeah.
And, the part where we got one, where the cancellation and we use chopping.
Yeah.
Can you do that with rounding to have an example of rounding?
Oh, okay, wait, you want me to carry this out using rounding?
Yes.
Okay. I'll do this in MATLAB. Okay, so I have square root of 6 plus h square root of 6. H, 5 digits, round, see what happens. Alright, so H is minus 4. Okay, so now I have square root of 6 plus H. Okay, so 5-digit rounding, so that'd be 2.4495. Okay, and then x2 is square root. Okay, then I have square root of 6. Okay, so x2 would be 2.4495 if I'm rounding. Whereas before I had 2. Oh, okay. Now I know why I'm chopping in here. So in fact, if I had 5-digit rounding, I'd get 0. Because both of these numbers would be 2.4495.
Can you go back to that? When you did, square root of 6 plus h, on paper, would we have to do 6 plus h and then have an answer and then have to do the square root of that?
Yeah, now, in this case, 6 plus 8 can be represented exactly.
Okay, so that's not necessary because of that.
Yeah.
But if the decimal digit of precision, if that was different, then it might be the case where we have to do that first and then get the answer.
Well, okay, I think this is what, I'm not sure this is what you mean, but let's suppose I still had 5 digits, but let's just say h was 10 to the minus 8. Now that's still representable if you choose the right exponent. If I do 6 plus h, that would become 6 because the h is too small. So yeah, I have to choose an h that was small, but not so small that it would get lost. Okay, any questions about this one? Here's another rate of convergence one. When I went overboard with Taylor remainder. Okay, so here you're told that the limit of this expression as h goes to 0 is 1. So to determine the rate of convergence, since it's converging to 1, what you need to look at is your function minus 1. So you have to subtract off the limit. Don't forget to do that. So then I put everything into one fraction, like over a common denominator. And now I have e to the h and cosine h both that need to be replaced by Taylor expansions. So right here is Taylor expansion for e to the h. And then right here is a Taylor expansion for cosine. And then make sure to include enough terms so that you get something that doesn't cancel. So if you find that everything cancels, you wind up with 0, you did not include enough terms. And what we see here is that a lot of things simplify. A lot of terms cancel, like the 1's cancel, the h's cancel, all the h squared terms also cancel. And after you cancel everything that you can, and also you can divide by h, this is what you wind up with. So you have a term times involving h squared, and a term involving h cubed. Now, here is, you keep in mind that the lowest power of h wins in terms of determining rate of convergence. Okay, so here I went overboard in terms of determining the constant in front of the h squared, that would work. But as early as here, you can see that what the answer is, that rate of convergence is big O of h squared.
Question on this one.
Yeah.
So, where
You
the
feeling
last
stuffy?
Not really.
inequality where it says, e over, like, the one right before that where you took out h to the second,
Yeah.
and then the one next to it where the h to the second is taken out, why is there not an h over 24?
Oh, because I'm assuming that h is less or equal to 1 in absolute value. So I'm upper bounding this.
Okay.
Yeah.
Okay.
Yeah,
So it's
I did gloss over some things.
So what's inside for the constant you can plug in for your h value.
Yeah. Yeah, so really what happened was, factored out the h, there was an h here, but it was less or equal to 1.
I'll make sure I understood.
Yeah.
Because obviously we wouldn't do that to the h to the squared.
Yeah.
So you only do that whenever there's take an h, factor of h's in all of them, and then whatever's left, you can up and down it.
Yeah.
For the constant.
Yeah, because it's okay to assume that h is less or equal to something, like less or equal to 1, because we really care about what's happening as h goes to 0. Yeah, because this expression, like, okay, if you were to like examine it for values of h, as h goes to 0, you would see it really is behaving like a constant times h squared. For larger h, it might not, but we're still h squared because of what happens when h is small. Questions on this one?
In general, you don't have to check if there's a constant.
No, I'm not. Yeah, you don't have to deliver the constant. Basically, your rate of convergence is going to be big O h to the something, and want to know if that power is right. Then you actually work with that. Yes. What? Oh, by the way, big thing there. Tomorrow, 1:20 p.m. is like the test of the national alert system. So your phone's gonna make a lot of noise. And there's one source that I saw, I was Googling about this, that apparently it will make the noise even if your phone is on silent. So I suggest, I have a 1 o'clock class. So I have to tell everybody, like, turn your damn phones off.
Like, shut them off.
Completely off. And then like, don't turn mine again for like another hour or so. And someone's gonna forget, the class is gonna be disrupted and wrong.
Wait, what's gonna happen at 1:20 tomorrow?
There's gonna be a text alert sent to every single phone in America.
What for?
That's a test of the emergency alert system. It's just a test, but you're gonna get some alert on your phone telling you that it's a test, but it's gonna make a loud noise. Yeah, so that's why you might wanna have your phone off. during that time.
During 120?
Yeah, or like, yeah,
So putting your phone on silent isn't going to cut it.
apparently not, I couldn't really confirm that.
It's like a tornado or like an Amber Alert, they override it.
Oh, people run silent,
Yeah.
that makes sense, but yeah,
One, two,
yeah, my phone's always on silent, so, yeah.
We're happy they do that.
Yeah. Okay, now, here's another Lagrange question. Here you're given 5 interpolation points. So you have a interpolating polynomial degree 4 for cosine. So I chose interpolating points that the y values work out fairly nicely. About 2 of the y values are 0. Cosine of minus pi over 2 and cosine of pi over 2 are 0. The other values are plus or minus 1. So we just work out these degree 4 Lagrange polynomials. Nothing to it.
Zero.
Yeah.
So the pattern still applies, it's just harder to read, because there's so much stuff going on.
Yeah.
Okay.
Yeah, there's always pies there. Sorry, not sorry.
That's all right, I just wanna make sure that like logically
Yes.
that.
Because computers don't care how the numbers work out. So, is there any questions?
Format rat.
What?
Format rat.
Oh, okay. Any questions about Lagrange? Which this will not be called forever. And finally, Newtoning. Because, okay, so here's your function, the exponential, you're given 4 interpolation points, so it's going to be a cubic polynomial. Your x values are 0, 1, 2, 3. So you'll list your x value, your y values. For this case, you pick the number of decimal places you want to use and stick with it. I guess you want to do that, not do the computations for you. Write down whatever it is. Okay. So then you generate your divided differences. So subtracting divided differences next to it, divided by the difference in the corresponding x values. Really, the example that I had earlier explains it better, and it shows what exactly what's being subtracted. Okay, and then take the top row of divided differences. There are 4 of them in this case. So the first one will just be by itself, a constant term, and then plus the next one times x minus 0, x minus the first interpolation point, and then plus the third divided difference times x minus 0 times x minus 1, which is the second interpolation point, plus the final divided difference times x minus 1, and then the third interpolation point, x minus 2. Leave it in this form, so I can see that you got the division form right. And that's all there is to it, because I haven't taught about error analysis yet. Or interpolation error is the next section. I have to remove that.
I think the end on an odd number, because I don't like odd numbers, but silly question number 7. For anything that can be plugged into MATLAB, do we need to indicate on our answers, like we can start part into MATLAB, or is that like?
No, I don't care. Okay. I wonder if I can squeeze it in here, provide a difference table. I might not have room, but okay. So right here, so this would be
Okay.
okay. So that's how this divided difference is obtained, by this minus this divided by this x value minus this x value. And then I continue that. So this would be one. And then this one is. That's how this column is.
Why did you put a minus sign here?
Where?
Okay.
Wait,
Oh,
whoops, that's a typo. Wait, there should be a 0 there. Yeah, so this minus this divided by the neighboring x value is 3 minus 2.
how do you get how did you get the other rows?
Of these,
Yes.
I'm about to do that. Okay, so here we take the divide differences adjacent to it. Divided by 2 minus 0. I feel like I'm gonna run out of room. Okay, this one's gonna be divided by 3 minus 1. And then the last one looks like I've run out of room. It's gonna be this minus this divided by 3 minus
3
0.
minus 0.
Yeah, that's where we all come
So there's not enough room for that?
from. Yeah, but, this goes off the page.
Yeah.
Okay, I'll put it down here.
Yeah, it's. Or just this. Well, I did.
That's the equation for balance.
But you didn't.
This minus this divided by 3 minus 0.
And all this is gonna be posted on Canvas?
Yes, Yeah.
Oh, okay, I guess I get to do some question number 8, slide. For the variable numbers, like the 2 minus 1, I get that first column, but for the second and further,
okay.
is for the 2 minus 0, is that saying like you're using those 2 rows and then before those 2 rows there was nothing? And then for the 3 minus 1, you're using the next 2 and before that there was 1.
I'm not sure exactly the question, but, okay. So this, considering this divided difference comes from these two that involve points 0, 1, and 2.
Yeah.
What we subtract are the extremal ones.
Divided by what?
The like, this involves points 0, 1, and 2.
Mhm.
So you want to subtract are the extremal ones, the last minus the first of the ones that were involved.
Also the ones that don't.
Yes, that too. Yeah, so first and last. Like, okay, the number one,
Slay. Okay, that makes sense.
okay. It does? Okay.
first and last did it.
Okay. Oh, man.
Yeah, I got my favorite one.
Well, class time is almost over. Right. Any other questions? I never had a few go full class. So,
Told you I would have more questions.
okay.
All over.
I do, but it's not really.
I have
Oh,
a homework
okay.
question.
I'm still stuck on homework.
Yeah, I mean,
Okay, all right, well, I'll stop recording anyway. And then I can stick around up to a certain point for